In this video, we'll talk about initial value problems and how they can be solved using antiderivatives. So initial value problems is sort of our first foray into what's called differential equations. And this is something that you can use these antiderivative techniques to try to solve. So an equation of the form dy dx equals f of x is what's called a differential equation. There are many other types of differential equations. This is one of them, but this is the main example that you will see in this class. The point here is you'll be given the function f, and you want to solve for the unknown function y. Since this is an equation involving derivatives, it's called a differential equation. However, based on our work from before, we know that more than one function solves this equation, right? If I have a function that I know its derivative, that determines it up to an unknown constant, up to this plus c that we had for all of our antiderivative problems from before. In order to get rid of that plus c, we give an initial condition. And this is the value of the function at one particular point. And so I say, here's a derivative, so here's the slope of the graph everywhere, that you can shift up and down however you want, just like we had for our general antiderivative. It's the same slope if you shift it up and down. However, I now tell you it must pass through one certain point, and that fixes which of these curves you have. You have a whole bunch of curves that could shift up and down and be the same slopes, but if I tell you one point on that graph, that fixes where the graph has to be. And so this combination of a differential equation plus initial condition is what's called an initial value problem. And the goal here is to find the function y of x that meets both conditions, namely its derivative is my known function f, and the value at a certain point is whatever given in the problem. Let's see an example of what this might look like. I want to solve the following initial value problem. dy dt is 3 square root of t plus 4e to the t, and y of 1 is 3. So let's start by finding the general antiderivative for this function here, right? Because the point is my function's derivative needs to be equal to 3 root t plus 4e to the t. So I can find the general antiderivative for that function and then use the arbitrary constant c to meet the initial condition. So if I take 3 root t plus 4e to the t, I can rewrite this as 3t to the 1/2 plus 4e to the t. And so then my function y of t is going to be the antiderivative of this, and then plus a c that we'll determine later. So I have the 3, t to the 1/2 needs to become t to the 1/2 plus 1 over 1/2 plus 1. Even though this is a fractional power, it still works the same way like the power rule did before. And then plus e to the t still becomes e to the t when I take antiderivatives. So 4e to the t, and then plus c. Simplifying this out is equal to 3 times t to the 3/2 over 3/2 plus 4e to the t plus c, or 2t to the 3/2 plus 4e to the t plus c. That becomes a 2/3 on top. And now I want to meet my initial condition. My condition said that y of 1 should be 3. Now I can plug in t equals 1 and see what c has to be to make this work. So if I plug in t equals 1, I will get y of 1, which I know should be 3, equals 2 times 1 to the 3/2, which is 1, plus 4e to the 1 plus c, which means that 1 equals 4e plus c, or c equals 1 minus 4e. I can then put that into here to get my final solution. Y of t is 2t to the 3/2 plus 4e to the t plus 1 minus 4e. And that will be the answer for that initial value problem. This gives you an idea what those problems are, what they might look like, and how you can go about solving them using antiderivatives.